In this lesson, we're going to explain how knowing more than one derivative at a point allows you to get a more accurate picture of a function. So the goal of this lesson is actually pretty simple, so let me just explain it. If you knew the value of a function at a particular x value, then all you really know is where the function goes through. If, however, you knew its gradient, you at least know that it's going in a particular direction. Now, as we said in the past, the gradient is the same thing as the first derivative. But in our lesson on the second derivative, we explained that the second derivative can be thought of as the direction of turning of the function. So knowing the second derivative allows you to get a more accurate picture of what the function looks like in this region. So in this lesson, we'd like to explore exactly what information the second derivative gives you about the shape of the function. So I've just made an important point right over here. The more derivatives you have, the clearer your picture of a function becomes. And this is actually really important when you want to try dealing with functions that are harder than the simple functions you've learnt so far. So to be clear, if you knew the value of a function at a particular point, and we assume that we're dealing with continuous functions, this sort of limits the range of functions that we could have. If we know the function value at this point, and we know that the function is continuous, we don't expect the function to suddenly jump up here. So functions around here are a little bit more likely, but functions up here become a little bit less likely. But for all we know, the function could just jump right up here because we don't know the first derivative. So the next thing we're going to do is we're going to imagine finding the first derivative. So I'm going to cover three scenarios here. First, I want to look at the case when the first derivative is exactly equal to 0. And then I'm going to look at the case where the first derivative is positive, and also the case where the first derivative is negative. Okay, so at this point we have no information about points immediately surrounding this area. But when we know the first derivative, we immediately know whether the curve is going down, across, or it's going up at this point. This really limits the number of possible shapes that each curve can take. So in the case where f-x is less than 0, we know the gradient is negative, but we don't know what it's going to do in the future. It could do this, or basically anything it likes. And the same goes for the case where f-x equals 0. You could have this, or it could just be a straight line. And obviously the same is true for f-x being greater than 0 too. You can have any of these as well. So if you look at these graphs over here, we're a little bit more sure of the shape of the graph than we were up here, but we still don't really know how the function is going to behave when we get really far away from this point. But as we said in the start, the more derivatives you have, the closer you're going to be to the actual function. So, of course, after looking at the first derivative, it only really makes sense to look at the second derivative. But I'm going to do this first for the case where f-x is greater than 0 only. Okay, so I've drawn three possible cases here because I want to allow for three different types of second derivatives. I first want to look at the case where the second derivative is positive, and then I want to look at the case where it's 0, and also the case where it's negative. So, as we know, when f double dash is greater than 0, the function is going to curve upwards. When f double dash is equal to 0, the function will not curve at all, and if f double dash is less than 0, then the function curves downwards. Okay, so now if we know the shape of this particular function looks a little bit like this, then we know more about how the function behaves as we get even further from this initial starting point. So as you can see here, by knowing the second derivative, the number of functions that we can have gets limited by a fair bit. I think the most interesting case is actually when you compare this to this. If you know only the first derivative, the function could go off wildly and do anything it likes. But if you know the second derivative as well, you know that the function stays still for a while and then it can go off and do what it likes later. And if we think about it, this function over here is increasing, but it's doing so at an increasing rate. This function's increasing, but it's doing so at a constant rate, and this function's also increasing, but it's doing so at a decreasing rate. The fact that we're using more descriptive words to describe the function should tell you that we know a little bit more about the function. So everything along this branch is increasing, and if the second derivative is positive, that indicates an increasing rate. If it's 0, that indicates a constant rate, and if it's negative, that indicates a decreasing rate. So now that we've talked about every possible increasing case, we should talk about this case over here. And we'd say this case is not moving right now, or that it's stationary. Okay, so it's not moving now, but that doesn't say anything about its future behavior. So as we said, it can either go up, down, or stay still. Again, just like we saw in the case over here, knowing the second derivative in the case where we have a stationary point allows us to restrict the movement of the function in a few different ways. So just like we saw in the last case, knowing the second derivatives allows us to estimate the values of the functions a little bit more closely. This function over here is stationary, but it's stationary and has a decreasing rate. This function has a constant rate, and this function over here has an increasing rate. So now that we've finished talking about all the stationary functions we can have, let's talk about all the decreasing functions that we can have. Okay, so just like we saw in the other cases, all of these functions are decreasing, but this one's doing so at a decreasing rate, this one's at a constant rate, and this one's at an increasing rate. And of course, this again limits the amount of possible functions that we could have. So as we said before, by having the second derivative, we can more clearly estimate the graph near the point, but as we get further from the point, the graphs tend to deviate. So given this information, we can actually classify the graphs into a bunch of different types. So for example, this graph over here looks a little bit like a maximum, and this graph over here looks a little bit like a minimum. So this immediately tells us that if our first derivative is 0, and our second derivative is negative, we have a maximum, and if it's positive, we have a minimum. Now of course this isn't really foolproof, because you could have a constant rate for a while and then the function could decide to go up on both sides. That would also be a maximum, but it could have a second and first derivative of 0. And this is the reason why I'd say that the best way to test for maximums or minimums is to find nearby points and make sure that the values both go down. Or in the case of a minimum, make sure that they both go up. Okay, now this is a fair bit of information, but I'd like to show you exactly how it's useful. We already know that if you have the first derivative, we can find the line of best fit to a graph, right? Well, if we have the second derivative, then in principle it should be possible to find the parabola of best fit to a graph. This is a really useful thing to be able to do, because if we're handed a random function, we can estimate its shape with nothing but the information about its function value, its first derivative, and its second derivative. So without further ado, let me go ahead and actually show you how we can do this for a particular function. So to make this clear, we'd like to find the best linear and quadratic approximation to this function over here when x is equal to 0. First, I'll start with a graph of this function. Now, as we said, we'd like the best linear and quadratic approximation to this function when x equals 0. Now, as you can imagine, the best linear approximation would look something like this, and the best quadratic approximation would look something like this. Okay, so I've labeled all of our functions. So f of x is our original function, L of x is the linear approximation at 0, and Q of x is the quadratic approximation at 0. So as you can see, the quadratic approximation is going to hug our function for a little bit longer than our line should. Let's begin by finding the equation of our line, because we already know that the line of best fit is just the tangent line. Okay, so we already know that the equation of any line is just going to be mx plus b. And of course, m and b are just two parameters that can dictate what the shape of the line looks like. Now, if this is going to be a good approximation at all, you better hope that the value of L of x is exactly the same as the value of f of x when x equals 0. Okay, well if that's the case, then we're going to replace all the x's for zeros in this function and all the x's for zeros in this function over here and make them equal to each other. Now of course, m times 0 is 0, and this 0 can just disappear. So by forcing the function values of both of these functions to be the same, we end up finding out that b is just the same thing as the number 2. Okay, and then we can just do this again. If we want L to be a good approximation to f, then we expect its derivative to be exactly the same as the derivative of this at x equals 0. If we want the derivatives to be equal, we actually have to find them first. So I'm going to go ahead and differentiate this function and this function as well. Okay, so to find the derivative of f of x, I've just rewritten it so that you have this power of half at the top. And then we're going to use the bring the power down rule. Okay, so the derivative of f of x is just this 1/2 x plus 4 to the power of minus 1/2. You would use a chain rule, but the derivative of the inside is just 1 here. Okay, so we want to find f dash 0. So if we replace all of the x's in this equation for a 0, then we could see that 4 to the power of negative 1/2 is just going to be a half. And a half times a half is just 1 on 4. Okay, so we already know that the right side is equal to 1 on 4, but we want the left side as well, so we have to differentiate L of x here. Now, you can hopefully see that the derivative of L of x is just going to be m, because the constant goes away, and so does the x. Okay, so since we know the value of m and b here, then we know that the best linear approximation to this function f of x here is just going to be 1/4 x plus 2. Okay, so since we've found this, let's go ahead and remove its working out, and then focus on the star of the show. Okay, so now we want to find the parabola of best fit to this particular function f of x when x equals 0. To do that, let's start with the general equation of a parabola. Now, as we said before, you're going to need the second derivative of the parabola. So I'm just going to go ahead and differentiate it twice, just so we have it. Okay, so we see that the first derivative of ax squared plus bx plus c is 2ax plus b, and then the second derivative is just 2a. We also want to differentiate f dash of x one more time, so we have f double dash x as well, because we're going to need that too. And we also want to know what the second derivative is equal to when x equals 0, so let me substitute that using my calculator. So we notice that the second derivative with respect to x at x equals 0 is equal to -1 on 32. Okay, so now we're actually more than ready to actually tackle this problem over here. For starters, we want the function value and the value of the quadratic to both be equal to each other when x is equal to 0. Now, as we know, the function value when x equals 0 is just 2, because the square root of 4 is 2. And the function value of q of x when x equals 0 is just going to be c, because both of these terms are going to cancel out. And just like that, we immediately find the value of c. And now we continue just like we did before. We want f dash of 0 to be exactly equal to q dash of 0, because we want the gradients to be the same. We can see that f dash of 0 is 1 on 4, and q dash of 0 is just going to be b, because this 2ax is going to cross out. So I bet you can guess what we're going to do next. We want f double dash of 0 to be exactly equal to q double dash of 0. But because there is no x in this equation, q double dash of 0 is just equal to 2a. And now to find the value of a, we just divide both sides by this 2 over here. And now, since we know the values of a, b, and c, we've actually found q of x, which is the best quadratic approximation to our function. Now, after watching this, I hope what I'm about to say will come as no surprise to you at all. If we just differentiate this again, and we differentiate this again and equate them, we'll actually be able to find the cubic of best fit, and then the quartic of best fit, and we could keep going for as long as we like. There is also something else that I want to say, so I'm going to get rid of all of this working out here. So I just want you to notice that the equation for the line of best fit actually appears in the equation for the quartic of best fit as well. And by looking at this, I hope this further reinforces the fact that every time I add a new derivative, I gain more information about the shape of the function. And now with this, we've actually completed our example. Now I alluded to this in my example, but if you find more than just the first and second derivatives, you can actually gain a lot more information about the function, and it is actually possible to differentiate your function as many times as you reasonably like. So the idea is that you can continue as far as you like into the future, and you can get better and better estimates of any function you like. Unfortunately, however, if you want to model real-world phenomena, it turns out that it actually gets harder and harder to predict the values of future derivatives beyond the first and the second one. However, if we stay inside the realm of mathematics where we can find as many derivatives as we like, we can actually generalize this as far as we want. In fact, the generalization of this method over here is called Taylor's theorem, and I'm actually going to cover it in another video, so tune in for that one if you'd like to learn more about this. But with this, we've actually completed this lesson. In this lesson, we found that if you have the value of a function at a particular point, then you don't have very much information about how it's going to behave in the future. However, if you have the value of the first derivative, then you know how the function is going to behave a little bit further into the future. And similarly, if you went ahead and found the value of the second derivative of the function, you can know how it behaves even further into the future. We use this information to actually help us find the parabola of best fit to a particular function. And then we said you could extend this to as many derivatives as you want to help you find the value of a function to an even greater degree of certainty. And as we said, there's a theorem in mathematics called Taylor's theorem that will help you do just that, which I'll show you in a future lesson. And given this information, I hope you can see how you could build up functions. In the future, you'll actually be able to use these principles to help you estimate the value of the function a long time into the future. And if you're able to estimate the value of complicated functions, you can use all the powerful tools of mathematics to help you analyze it. So with this, we've completed our discussion of building up functions.